So last time we were talking about cubic splines, and cubic splines are cubic functions that go between each individual data point, and they have three main conditions. That is that each spline is continuous at each xk, its first derivative is continuous at each xk, and its second derivative is continuous at each xk. So we started to define the cubic spline interpolant. We had n+1 points from 0 to n, and they are in order. We then went and defined the kth spline. So that spline is on the interval xk to xk plus 1. So there are n spline interpolants. So we defined them. So each one has a constant, and then each one is a cubic polynomial about the xk. So that at xk, it is the value sk naught, which is actually the y value. So as you can see, xk naught is the y value for each xk. And so this is what we have. So s of xk is exactly yk. So this yk turns out to be sk0. Okay, so that's what that is. And then something is wrong. That should be 0 to, no, that's right, 0 sk. Why do I have n+1? That's sk of sk is equal to yk. Oh, that's n+1 conditions. Okay, n+1 conditions. Then the first derivative, well, the function is continuous. So that's what we said, sk is continuous. And then it has to be continuous at all the points. And that should be up to k0 to kn-1. Then we have the first derivative is continuous and the second derivative is continuous. So that gave us 4n-2 equations, but we have 4n-2 we have 4n unknowns. So that means we need two pieces of information still in order to be able to uniquely define our splines, and those are going to come in the fact of the boundary conditions. So we looked at our splines, and here, right here, we said that hk is simply xk plus 1 minus xk. So that's how we would be able to define hk. And mk are the slopes. So mk is simply the second derivative of the entire spline at xk. Okay, so we started there and we integrated. So that thing we knew was a linear function. So we made it a linear function using our Lagrange interpolant, Lagrange interpolating polynomials. Thank you. Okay, and then we integrated that to get our the first derivative, and then we proceeded to integrate one more time to actually find out what that was, sk. And then we said that this little piece at the end is simply a linear function, and we chose to make our linear function something that looks like this. And the reason why we can make it look like that is because that still itself is a linear function. If you put in xk, you get, let me see, something's not right. Yes, there is a mistake here. this should be P of xk minus x. Okay, I knew something looked funny. P of xk minus x, and then qk times x minus xk. That way, it works out very nicely that if x is xk plus 1, you get qk, and if x is xk, you get pk. Okay. So now that we know what this function looks like, again, here is my typo. I see it one more time. This is supposed to be an x. Excuse me. Okay, now it is correct. That's why I like to go back over the notes from before we jump into the new material. And so we were saying now you can go back into those equations and substitute xk and xk plus 1 into the equations, and we know what we're supposed to get. So if we put in xk, we're supposed to get yk. And when you do sk of xk plus 1, you're supposed to get yk plus 1. Okay, so what makes that so nice is now we actually have a system here where you can actually solve. We know yk is known, mk is known, hk is known. The only thing that's not known is pk and qk. And so therefore we can solve for pk and qk. All right, so this is where we stopped. Okay, so now we want to go through and continue to derive what we need. All right, so for our mk and mk plus 1 unknowns, now remember mk and mk plus 1, those were the second derivatives of the function at particular xk. Okay, so mk is the second derivative of xk plus 1. And I'm sorry, that was mk plus 1, and mk is the second derivative at xk. So once we know those, then we can solve for everything. So let's find them. So these are unknowns. Then just want to be able to turn my fan on and off when I need to. Okay, so therefore sk of x. Well, we know what this is. This is mk over 6hk times xk plus 1 minus x cubed plus mk plus 1 all over 6hk times x minus xk cubed plus yk over hk minus mk hk over 6 times xk plus 1 minus x plus yk plus 1 over hk minus mk plus 1 hk over 6, and this is times x minus xk. So this thing right here That's PK. And this thing right here that is QK. So we just solve for PK and QK. All righty. So to find MK, we want to use the following. We're going to take the derivative of the kth interpolant, cubic spline interpolant. And when we take the derivative of that, we get M, so the 3 comes down, so you get MK over 2HK times XK plus 1 minus X squared plus MK plus 1 over 2HK times X minus XK squared. We're taking the derivative with respect to X. So the only thing that's going to come out this next term is minus YK over HK minus MK HK over 6. And then what we get from this next term, which is plus YK plus 1 over HK minus MK plus 1 HK over 6. Okay. All right. So now let's evaluate that at XK. So SK prime. So I'm evaluating this at XK. So when I evaluate it at XK, when I put XK in here, this thing becomes HK. So I'm going to put XK in here. So when I put XK in there, that becomes HK squared. Okay. So therefore, I'm going to end up with MK. Why is it negative? I am missing, oh, because this is negative. Forgot my negative from the chain rule. Okay, so this becomes minus MK HK over 2. Okay, when I put XK in here, that term drops out. And so then I'm still going to subtract off what I already have here, which is YK over HK. I'm going to add on MK HK over 6. Then I'm going to add on YK plus 1 over HK. And then I'm going to subtract off MK plus 1 HK all over 6. Okay, so let's simplify that. So I can simplify that to get SK prime at XK. Your question?
Yeah, this last line, how did you get that?
Okay, so did you get the line before? You understand this line?
Yes.
Okay. All right, so what I did was I put XK in this equation above. So when I put XK in here, this becomes XK plus 1 minus XK, but that's just HK.
Yeah.
So I get HK squared.
Okay.
And so HK squared over the HK just gives me HK.
Okay. Oh, okay.
And then the next term, when I put XK in, I get 0.
Yeah.
And then I distributed the minus on this second term, the third term. And then I just wrote the fourth term as it is.
Okay.
Okay, thank you for asking. So now I get negative MK HK over 3 because I combined two terms. Then I'm going to get minus MK plus 1 HK over 6. And then I'm going to combine these last terms to get YK plus 1 minus YK. And they are both over HK. Okay. All right. So now we want to find MK and MK plus 1. All right. So we're going to replace, and this is where I remember again as a student, I remember learning all of this. And this is the step that threw me off and made cubic splines so impossible, but it's really not that difficult. But it was when I was learning it. So we're going to replace K by K minus 1, all right, in SK prime.
So why are we replacing it with K minus?
I can't hear you. What'd you say?
I say why are we replacing it with K minus 1?
Because remember the two functions have to be continuous.
Okay.
So we can find, if we find what SK minus 1 is,
Yeah.
SK minus 1 at XK has to be the same as XK at XK.
Okay.
Yes. Okay. So therefore, I want to keep that equation, try to keep it visible. I don't know if I'm going to be able to. I could do something to y'all, but y'all wouldn't like that. And that was copy the whole equation and just change everything. Let me just rewrite the whole thing. So I get SK minus 1 now, prime, at X. I get negative MK minus 1. And then this is still over H now, 2HK minus 1. This doesn't change. This was XK plus 1 minus X. It's now XK. Okay. This was MK plus 1. It's now MK. This was 2. This was HK. It's now HK minus 1. And this was X minus XK. So it is now X minus XK minus 1 squared. Minus YK minus 1 over HK minus 1. And that's going to be then subtract off MK minus 1, HK minus 1 over 6. Then I'm going to get YK, that was YK plus 1, over HK minus 1, that was HK, minus MK, HK minus 1 over 6. Okay. So now I'm going to evaluate this at XK. So SK minus 1 prime at XK. We're going to put in XK. So notice when I put in XK, the first term drops out. So I simply get MK over 2HK minus 1. And then I'm going to get XK minus XK minus 1 squared minus what the minus this other stuff. Okay, I'll give you a minute to copy that. Just put that line where it belongs. Okay. So I can factor that out and simplify it. And so now when I do that, I'm going to simplify this one the way I simplified the other one. And so now I get SK minus 1 prime at XK. This is the simplified version, guys, is MK over 3 HK minus 1 plus MK minus 1 over 6 HK minus 1 plus YK minus YK minus 1 over HK minus 1. Okay. So now I have two equations. All right. So the first one is SK prime at HK. So this is the first one. Okay. So now I have those two equations. Okay, so Jenna,
Ma'am?
you asked me, why did I do that? And
Yes.
I said, we have to remember the properties. Okay. So
Yeah.
let's recall property. I want to say, which one was it? Property 4. Let me see, what did I call it? Yes, property 4. The first derivatives are continuous.
Okay.
Okay. That is sk prime at xk plus 1 has to equal, sk plus 1 prime at xk plus 1. So that translates into sk minus 1 prime at xk has to equal sk prime at xk. Okay, so now we got to set these things equal. So now we get negative mk over 6 times hk minus mk plus 1 over 6 hk plus yk plus 1 minus yk over hk has to equal mk over 3 times hk minus 1 plus mk minus 1 over 6 times hk minus 1 plus yk minus yk minus 1 over hk minus 1. All righty. So now we get 1/6 mk minus 1 hk plus 1/3 mk times hk plus hk minus 1 plus 1 over 6 mk plus 1 times hk is equal to yk plus 1. Sorry. That should just be yk minus yk minus 1 over hk minus 1 minus yk plus 1 minus yk over hk. All righty. So now this becomes a matrix system. Okay. So we end up with something's not right. Oh, we multiplied everything through by 6. That's what I do. I multiply everything through by 6. So then I get hk minus 1. That multiplies mk minus 1 plus 2 times hk plus hk minus 1. That multiplies by mk plus hk times mk plus 1 is equal to 6 times the right-hand side, which was the y case. All right, so the unknowns are the MKs. So now I have MK minus 1, MK, and MK plus 1 are my unknowns. K equal to 1, 2, all the way up to N minus 1. So now I have N minus 1 linear equations. And N plus 1 unknowns. So I have to figure out what to do about M naught and Mn. All right. So we get 2 additional equations from the endpoint constraints. And then we're set. Okay. All right. So if you're not sure what this means, we'll have an equation. So let's say we have N is equal to, let's say N is equal to 3. Okay. Then the first equation would be H naught M naught plus 2 times H naught H1 plus H naught M1 plus H1 M2 is equal to right-hand side 1. Then you would get H1 M1 plus 2 times H2 plus H1 M2 plus H2 M3 is equal to right-hand side 2. Let's jump. Yes. So this is going to look like H naught H1 0 0 H1 2 times H1 plus H naught H2 0 I think that's it. I don't think there is any more. That's it. But I have to tell you something, got to give you some information about M0 and M3, because I have two unknowns that are M1 and M2. Okay, so let's look at the endpoint constraints. All right. So we know SK of XK is YK. We know SK prime of XK is equal to negative MK HK over 3. We just did this. Minus MK plus 1 HK over 6 plus YK plus 1 minus YK over HK. We just figured that out. And S double prime K at XK is MK. Okay. All right. So there are two types of cubic splines that we can talk about. All right. So the first one we want to talk about is a clamped cubic spline. Okay. So for a clamped cubic spine, you need to specify S0 prime at X0 and Sn minus 1 prime at Xn. All right. This one, that one gives M0. And this one gives Mn. Okay. So once you find those, then you can put those into the equation. So now we had S0 prime at X0 is going to be minus M0 over 3 H0 minus M1 H0 over 6 plus Y1 minus Y0 all over H1 H0. Okay. So from there, once I tell you what S0 prime of S0 is, then I can solve uniquely for M0 in terms of M1. So that's going to give me M0 is equal to 3H over H0 3 over h naught times y1 minus y naught over h naught minus s naught prime at x naught, which we just supplied to the problem, minus m1 over 2. So therefore, in the equation, you can put m naught back in here. So m naught now can go back in here. And that eliminates the need for this column because m naught is in terms of m1. So now once you find m1, you can find m naught. We do the same thing for mn. Okay, so for mn, we have Sn prime, Sn minus 1 prime at xn.
Excuse me, ma'am.
Yes,
So anywhere we see m naught, we have to replace it with 3 over this.
I can't hear you. What are you saying?
I said in the elimination, anywhere we see m naught, we replace it with this.
Yes,
Yeah. Okay.
yes.
Okay.
So m naught would go in here. So
Okay.
when m naught goes in here, then what you do is anything that has a m1, you combine it with the m1 term, and anything that does not have m1 or m2, you throw to the right-hand side. Okay. And then this is mn over 3 times hn minus 1 plus mn minus 1 times hn minus 1 over 6 plus yn minus yn minus 1 all over hn minus 1. So now you can find mn. So mn is 3 over hn minus 1 times s prime of xn, and that should be s n minus 1 prime of xn minus yn minus yn minus 1 over hn minus 1, and the bracket minus m n minus 1 over 2. So now I can take and replace everything in mn by, in this case, m3. I would replace it right here, and that will eliminate the need for this one. So now I end up with a 2x2 system of equations, and I have just those unknowns. Okay. So that's what you do if you have a clamped cubic spline. Okay. You could have a natural cubic spline. Okay, and this is considered a relaxed curve. All right, so now you must specify that S naught double prime at X naught is equal to 0, and Sn minus 1 double prime at Xn is also equal to 0. So when I do that, the first one is going to give me that M naught has to be 0. And this last one gives me that Mn is 0. So now again, you go back, put that into your equation here. And so therefore, you end up with something very simple to solve. So if it's only if it's 0, 1, 2, and 3, then you end up with a simple 2 by 2 matrix. We know how to find the inverse of that. Take the determinant, solve for M1 and M2. It's easy when it's 3 points. Okay, nice and easy when it's 3 points. When it gets to be 4 points, then you're solving a 3 by 3 system. Not bad, but it's still doable. Okay. The last thing we can do is extrapolate S double prime of X to the endpoints. So you're going to have to do the first 2 methods in the homework. Okay. So okay. So I have this point. Here's M naught. I have this point. This is M1, which is equal to S1 double prime at X1. And then here's the point M2. And this is equal to S double prime. Oh, I did that wrong. So I'm on the left-hand side, I have those 3 points. So I want to do extrapolate. So I'm just going to do a relationship between the slopes M1, M2, and M naught in order to figure out what M naught is. So on the left-hand side, the ratio of M2 minus M1 divided by X2 minus X1 has to equal the ratio of M1 minus M naught to x1 minus x naught. And then I just solve for m naught. And that gives me m naught is m1 minus h naught over h1 times m2 minus m1. So now I would take that and put that in the equation. Okay. And then if I'm at the other end, use the same technique. At the other end. To get mn is equal to mn minus 1 minus hn minus 1 over hn minus 2 times m n minus 1 minus m n minus 2. Okay, any questions about that? All right. Another option is that the second derivative at x is constant. Okay. Try again. Here she is, babe. Is constant near the endpoints. And you say m naught is equal to m1 and mn is equal to mn minus 1. And then the last option is you specify s double prime of x at each endpoint. And of course, for any cubic spline, guys, you'll be told what to do. So m naught would be s double prime, s naught double prime at x naught, and mn would be Sn minus 1 double prime at Xn. Okay. Any questions? All right, so this is going how, so here's an example. Um, So now I want to consider this equation again. Okay, so that's our main equation. Okay, so this is the main equation. I'm just recopying it just so that we can see it again, because if we don't remember it, there it is. Okay, so that's the main equation. All right, so we're going to take the first equation, H naught. Oh, okay. Let me call this right-hand side. I'm going to give it a name because it's getting on my nerves. I'm going to call the right-hand side U1. Why am I calling it U1? I'm calling it UK. Yeah, I'm going to call it UK. Okay. So now, okay, make life easy. Okay, so the first equation, we have H naught M naught plus 2 times H1 plus H naught M1 plus H1 M2 is equal to U1. So we're going to get 2 H1 plus H naught M1 plus H1 M2 is going to be U1 minus H naught M naught. Because now we find M naught, right? Minus H naught M naught. So notice how we were able to eliminate M naught from our system. Okay, so this is equation 1. Okay, equation 2 is going to be H1 M1 plus 2 times H1, nope, H2 plus H1 M2 plus H2 M3 is going to equal U2. Then we're going to get H2 M2 plus 2 times H3 plus H2 M3 plus H3 M4 is U3. And we keep doing that until we get to the last equation. Which will be hn minus 2. Thank you. Mn minus 2 plus 2 times hn plus hn minus 1 m, this was m minus 2. That should be m minus 2. Okay. This is m minus 1, which means this would be hn minus 1, and this one should be hn minus 2. And then this should be hn minus 1 mn is equal to un, which we're going to rewrite as 2 hn minus 1 plus hn minus 2 times mn minus 1 plus hn minus 1 I need that first term. I do need this. This is hn minus 2 mn minus 2 plus 2 times hn minus 1 plus hn minus 2 times mn minus 1 is equal to un minus hn minus 1 mn. Woo, Lord have mercy, that was hard. Okay, so we're going to have all these intermediate, these are all the intermediate equations. Then our first equation is going to look like this one. And our last equation is going to look like this one. So now we're going to end up with a tridiagonal matrix. Okay. That's going to look like B1, C1, and nothing. A2, B2, C2, and nothing. A3, B3, and C3, and all zeros. And that's going to continue until we get to an minus 2, bn minus 2, cn minus 2, and then we're going to have an minus 1, bn minus 1. And so that is a matrix And then that gets multiplied by the vector M1, M2, M3, all the way down to Mn minus 1. This last one should be Un minus 1, not Un. It's Un minus 1. Okay. And that equals the right-hand side. And these should all be, this should be U2, U3. Yeah. No, it's not. That is U1 minus H naught. This one is U1 minus H naught, M naught. This one is U2. This one is U3. All the way down to UN minus 1 minus HN minus 1 MN. And now you just solve. Okay. And then when you're done, you have your cubic spline. And remember that S, so this is the big thing. You have to remember that SK of X is its defined spline on its interval. And so this is SK naught plus SK1 times X minus XK plus SK2 times X minus XK squared plus SK3 times X minus XK cubed. So once you learn, and this is on the interval XK to XK plus 1. Now, once you learn your M's, gotta go all the way back to the beginning. I'll get ready to say I'm missing something. Okay, I'm missing something. It's on the next page. I was a little confused. Sorry, guys. I'm missing something. Okay, now that you know all your M's, you got to do that. Okay. So, note. It's a theorem. The system of linear equations are non-singular. So therefore, the matrix is invertible, so you'll definitely get a solution for any partition okay. All right, so the only thing that's left, we got to solve for these. This one we know. We still have to solve for this one. We still have to solve for that one. And we still have to solve for that one. So we're almost done. So SK of XK is SK naught. And that's YK. Yay, one's easy. SK prime of XK is SK1. But this is negative MK HK divided by 3 minus MK plus 1. I knew we had done it already. I just couldn't find it. Over 6 times HK plus YK plus 1 minus YK all over HK. Okay, and then the second derivative, SK double prime at XK. Well, this is SK2, so now you know what that parameter is. And this one is just, I'm sorry, this is 2SK2, because you got to take the derivative, so you get 2 times SK2. But we know that that's just MK. That's what we called it. So therefore, nice and easy, SK2 is equal to MK over 2. And lastly, I don't have enough time. We're out of time. Okay, I will define the last part, SK3, first thing on Thursday. And then we will be moving into our next module. Okay, any questions, everybody? I know that was, cubic splines are heavy duty, but they're doable. They're doable. Okay. All right.
I have a question.